Okay, so let's get back from where we stopped the last lecture. I didn't manage to finish everything, but we can continue from there. That was essentially presenting the Markovian master equation, right? And we were dealing with this class of completely positive trace preserved maps, and imposing some conditions to this class of maps, we would lead to this Markovianity or the Lindblad master equation. That was the goal, right? Okay, so now everybody is really arriving. Okay. So essentially, what we saw is that we always have a map that translates any initial state to a final state that can be written in the Krauss decomposition, operator sum decomposition. But then if we impose these two very strong, in some sense, conditions, the first one is that we impose that the maps, it's a continuous map along all of the trajectories for all of the initial states. And moreover, if we impose that the map has no memory, in other words, if you act the map along any time of your trajectory, it does depend only on your specific configuration at that time. So it does not know if you came from this initial state or the other initial state. It just knows the local information that you give to the map. And this translates somehow in the irreversibility of your system, no memory from the past, and consequently, we can always write the full map for the full evolution of any initial state as these divisible maps decomposition, okay? And this is what we call as a Markovian master equation or a Markovian map. Now the goal is to obtain, let me say, the Lindbladian form for this class of operations. So the first step then is that it's going to be simpler for us to write down the maps for each one of the time steps in terms of the generators of the group, okay? So we write down the map for any time t up to t plus some delta step as some exponential of, remember that this is a super operator, so this is going to be the exponential of a super operator times the time step that you're dealing, okay? So then let me say that I'm going to use this notation of a double hat for super operators in order to not to confuse with just linear operators. And the goal is to obtain how is the differential equation that drives my dynamics towards all of my evolution. So the goal is to obtain essentially the master equation of how my state at any time t evolves when I look for infinitesimal time steps, okay? And now we are going to do a lot of mathematical manipulations to obtain this guy here. So this guy is just the limit of infinitesimal time steps of my state evolved for an infinitesimal time step minus my state at time t divided by dt, okay? And I can write down any infinitesimal time step for my state in terms of my map, okay? So this is just going to be the limit when dt goes to 0 of exponential super operator dt minus the identity applied to my initial state divided by dt, okay? So this guy here is just the application of my evolution operator into the previous time step, and this other one is just because I'm just keeping this guy here. But then, since we're looking for a very small time step or a continuous time step, we can just make the Taylor expansion in first order for my exponential, and then the only thing that's left at the end of the day is my super operator acting over my state, okay? And then we already see the shape or somehow the Lindblad master equation appearing here, right? Because the Lindblad master equation, I don't have in the slides anymore, at least not in the beginning. It's just that the time evolution or the differential equation for my quantum system is just driven by the Lindbladian generator over my quantum Hilbert space, okay? And then we can see what's the specific form or the structure of these superoperators here. For this, there are many different forms to do this, let me say. One way that I find very nice and a bit simpler is looking for the cross decomposition again and see how it should be in order to satisfy these conditions here. So let me just write down again this equation here in a different form, where I say that essentially what the differential equation says to us that my next state after the evolution is just my state at times t plus some infinitesimal time step and my Lindbladian acting on my state. Double hat. Okay? And on the other side, we know that any evolution or any completely positive trace preserve map can be written in terms of a cross decomposition that we discussed yesterday, okay? We can also write any state at times t plus dt, I'm sorry, okay, as a sum of my corresponding cross operators acting in my state at times t. Okay? We have these two different views of the same evolution. And then we can try to understand what's the shape or the structure of the cross operators in order to match for the corresponding Lindbladian superoperator. Okay? So we see, for example, that the cross operator, they can be either in first order in delta t, okay? In zero order in delta t, in order to keep this guy here, or in order half on both sides, in order also to keep the first order in my corresponding Lindbladian superoperator, okay? So I have essentially two possibilities for my cross operators without saying anything about what exactly are these guys here, microscopic in terms of spin or anything like this. We know that there is one possibility that they need to be the identity, in such a way that when I apply the identity to both sides here, I recover this first guy here, okay? The second possibility is adding to the identity a first order in dt times some general arbitrary operator in here. In such a way that when we act on both sides here, we are going to have identity times identity. We get this guy here. But then we can have identity times g and order dt. Okay? Then we have one of these guys that should be here in the structure of the Lindbladian. Of course, that we also have these guys appearing twice, order dt squared, but then we can neglect because we are always getting the limit of infinitesimal time steps. Okay? The second possibility is having some other operators that has square root of dt on both sides, okay? In such a way that we have essentially also order t appearing in my Lindbladian superoperator. Okay, so it's pretty simple, the steps or the considerations that we do here. But remember that cross operators, they need to fill all of my Hilbert space. So we need to satisfy that the sum over all of my cross operators, they need to go towards the identity, okay? Because of the probabilistic nature or the interpretation as physical measurements being done in this system. And this thing here is going to determine a few properties of what are the G and the L operators in my corresponding master equation, okay? So we can just expand this guy here, and we see that the first term is just, so it's going to be m dagger 0, m0, plus m dagger k, sum, right? It could be any guy, different from 0, mk. And then we have the first one is just identity plus dt g dagger, and identity plus g dt g. I'm sorry, I think that someone is saying in the Zoom, how can I access the... Can you repeat the question, please? I think that someone is talking by the Zoom, if I correctly understand. I think that there's someone making some questions in the Zoom link. Ah, okay, okay. So it's the machine that's not understanding me. Okay. Okay, so let's continue then. So then expanding M0, M0, we have this first guy here, and the other to appear as order dt, and then we have L dagger k, LK. Okay. Then we can, of course, put all of the orders of 0 order in dt, and then we have first order and dt, and then it's going to have g plus g dagger plus these guys here, sum over k, L dagger k, LK, and then we have some further orders of order dt square, but then we simply assume that this is not important when we take the infinitesimal time step limit, and we only need to be sure that this first order here, it goes to 0. So in other words, it is saying that the Hermitian part of my G operator needs to be equal to minus the sum of all of these L dagger K, LK operators, right? So when I take any operator plus the Hermitian conjugated, I'm just taking the Hermitian part of the system, right? Of this operator. So then it makes natural for us to decompose this G operator in terms of its Hermitian and non-Hermitian, such that we put explicitly this constraint to this Hermitian part. So we just decompose G as some Hermitian. Let me call the Hermitian part is just called by K, and an anti-Hermitian part, and let me call as minus IH, in such a way that both K is Hermitian, H is also going to be an Hermitian operator, but since we are putting here the I sign, it means that it's an anti-Hermitian operator. And the condition, of course, that I'm putting H here, also with a big bias, that this is going to be the Hermitian operator in my Lindblad master equation. But then what the constraint is saying to us is that K operator needs to be minus half the sum of L dagger K, LK operator. Okay? And then we are essentially done with the Lindbladian master equation, because now we have the conditions on this set of cross operators, and we just need to substitute in the main equation and see what's the corresponding superoperator for the Lindbladian. Okay? Because if you have a square root of dt term here, for two reasons. The first is that you can always put in the other cross operators. And also you're going to have essentially square root of dt appearing in this first equation here, which I would say that doesn't make sense, right? Because then you have identity on one side that is going to multiply the square root of dt, but you don't have really these contributions to the main equation. Okay? So putting back or substituting in the main equation, we have then that my state at times t plus dt is equal to all of this guy here, but now putting explicitly the shape of my cross operators, I plus g dt, my state at times t, I'm sorry, order dt, sum over k, lk, rho, lk, dagger, okay? So again, so this we just get the identity for the first term here, that is just my state, and then at order dt, we are going to have this guy here. That is g applied on the left on my state, but then we have a g dagger applying from the right, plus rho g dagger, and plus the rest of the sum here, sum over k, lk, rho, lk dagger, and plus some orders of dt square that I ought say that is going to be negligible. And then I just need to substitute g is given by this minus sum here, but also some other contribution that is minus I, the Hamiltonian, okay? And then it's not going to be hard to see that the corresponding terms that's going to appear here is minus IH multiplying on the left, and then minus, I'm sorry, this is J dagger, and then plus IH rho multiplying on the right. So the first term here is going to apply minus I, a commutator of the Hamiltonian times my state. But then we also have the contribution of minus sum on the left and minus sum on the right as well, okay? Then we also have, on top of these terms here, sum over k, lk, rho, lk, dagger. These sums on the left and the sums on the right, that is just going to be the anti-commutator of L dagger k, lk over my state, okay? And all of this guy here is essentially what we were looking for, that is the Lindbladian superoperator. And then we have all of our GKSL master equation. Okay. Okay, so now we're a bit better on time. And then it becomes as an exercise to review that simple example of amplitude damping of a single atom that has some spontaneous decay. But now in the language of a Lindbladian master equation. That is essentially, now we have a dissipator, or one Lindblad jump operator, that essentially what it makes is that with some decay rate gamma, what it does to the spin is just applying the ladder decay operator over it. And you're going to see that we recover essentially the same phys that we had there for the Krauss decomposition and the full analysis of my system, okay? But then it becomes as an interesting exercise to play after. Yeah, so this is interesting. I mean, an L operator is a possibility for your master equation, okay? And then you can play, I mean, you can forget about some sense how this L operator appear here. But assume that you have this specific type of dissipators, what are the consequences? But essentially anything that you put here is okay. So the G can be anything, but it means that K, it needs to be related to the L operators in this specific form. And this other part here, the H, is really a Hermitian operator. And it's essentially, when you have the coherent part of Lindbladian, is going to be the Hermitian part of the Lindbladian, okay? So this has a strong constraint that needs to be physical Hamiltonian, in the sense, but this can be mathematically anything that you want. Okay, okay, so then how can we exploit a few of properties of this Lindbladian superoperator. Because again, this is not a linear operator, it's not so simple to handle as well. And I think that there was also some question about some universal properties of these superoperators. And then the way that we can address some of its universal properties is trying to understand the spectrum of this guy here. Just like when we have a Hamiltonian, if we understand the spectrum of the Hamiltonian, we can understand more or less how it's going to be the dynamics or some physical properties. We can also do the same thing for a Lindbladian superoperator. But remember, this is a superoperator. It's not easy to argue what are eigenstates, what are eigenvalues for a superoperator. And we do what we call as a vectorization of my superoperator that translates a superoperator again to a linear operator. So we decay one level of complexity for this guy. And also linear operators are going to become vectors. That's the main idea. And we cover the same analysis that we used to have in closed Schrödinger-like evolution. Yeah?
So far, this general form, it's not restricted to Markovianity, right? Or it's completely general?
It's restricted to Markovianity because we are assuming that the full map can be divisible in this following form. So we assume that for each one of the times, we can have a local map that acts for any initial state, that acts for any input state. It does not depend on the past, for example. Okay? So that's the Markovianity. And that's what we call, sometimes we see that Lindbladian, people say that it's a time-local master equation. Because it depends on only on the time properties, the local time properties of your system there. Okay?
Yeah, but technically, where we see our derivation because of the exponential or
yes, so essentially, you're saying that your map at times t depends only on t, nothing else. It does not depend on previous time, for example. Okay? And then you have something that depends only on time step, okay? And the Lindbladian that depends on t. Okay? I just left out this t here, but it's implicit that these Lindblad operators and the g, they also depend on the specific local time. But that's the only dependence on my superoperator. Okay? This is a very strong constraint, of course. Okay, so in order to understand a bit better, or in simpler form, vectorization, the general properties of these guys, we do what we call as vectorization. So essentially, we are aiming at mapping a superoperator now to a simpler linear operator, and then I just decay one hat of this guy here. Just remember that this now is an operator. And also, I put in this form here. Okay, no, just without the hat. But at the same time, if I do this type of vectorization, my density matrix, that is a linear operator, is going also to decrease one level of complexity, then is going to become a vector. Okay? And then I'm putting a double arrow here, just to say that it came from this vectorization process. But now this is a vector, and this is a matrix. And we know how to deal with vectors and matrices in order to obtain eigenstates and eigenvalues. How we do this? There are many different equivalent forms, in some sense, that leads to the same eigenstates. But one very simple that I like to use is just saying that the vectorization of any linear operator in my Hilbert space, I just need to make a ket bra to become a ket or a vector. So you can just make this simple modification where the bra here becomes a ket, and then the ket goes to the right side. Okay? Of course, that you see that here you have a linear operator that lives in a Hilbert space with some dimension, right? Dimension, let me say, dimension of my system. And then when I do the vectorization, I'm mapping this operator into a vector, but now the vector is the tensor product of Hilbert space times Hilbert space. So I'm mapping a smaller Hilbert space into an extended one that is twice the size of the original one. That's the price that I need to do to decrease the complexity of superoperator to a simpler operator. Okay? So in general, let me say, yes? No, this is a bijective map. So you can always go and come back. There is no issue also. Yeah. So then for a general state, that is a sum of C, ij, ij. Okay? If I do the vectorization of this guy, that is just in notation that we have is the vector, is just going to become C, I, J, J, I. Okay? Very simple. In practice, if you have a matrix that is your guy here, let me say A, B, C, D, when you make the vectorization of this guy here, is just this big vector that now lives in a larger subspace, 2 times 2, then you have a 4 times 1 vector. And I mean, if you want to code or make the numerical algorithm for this, you just follow this ordering here of first going down and then go to the second column, then go down again, and the corresponding is just this guy here, A, C, B, D. Okay? Then I have a vector. Important properties that we are going to use to derive the diagonalization of this guy. So the first one is that in my space of linear operators, we have a notion of distance between 2 density matrices, right? And we know that the distance, let me say, in the Hilbert-Schmidt space is just given by the trace of the first operator to the second operator, and then you just take the dagger of the first one. Okay? If you translate this distance between operators to my extended vectorized space, this is just going to be what we expect. This is going to be the inner product of my A operator to my vectorized B operator. So we are mapping inner products to inner products in both of the space in order to have these notions preserved. So in particular, one thing that's going to be very simple, but it's going to be very important, is that if I just take the trace of any operator, let me say I take the trace of my B operator, I can always put an identity here, okay? And then using this equality here is just the trace of any operator in the vectorized space is just the inner product of my vector identity to the corresponding state. Okay? It's going to be more clear why this is going to be an important property. And a second good property is that, and this one I'm not going to show where it comes from, is that if you have the vectorization of higher order product of operators, then it's just getting the third one, the transpose of it, then you make the tensor product of the first one, and then you act in the guy that was in the middle. Okay. So I don't know of any simple form to prove this relation. The simpler way that I would suggest is that just expand this product here and make the factorization. Then you expand this product here and see if they match, and they do match. That's the easier, perhaps rough way to prove this relation. Okay? For sure, there might be some smarter forms to do this, but if anybody knows, let me know, because I'll be curious as well. So why this is going to be enough at this moment? Because now we can make this map here, right? I can map my Lindbladian superoperator into a simpler form. Because the linear Bladder superoperator, it has operators that act on the left, operators that act on the right, and operators that act on the left and the right at the same time. And with this formula here, we know what are the corresponding vectorized form of this guy. I'm sorry. Okay, it's this guy here. Okay? Because we always have my density matrix appearing in the middle of my Lindy-Bladder master equation. We can always make this. Either you put identity on the right or identity on the left, or it's already in this form. L, rho L is already in this form. And then you see that this guy here, that's going to be the density matrix, is going to be a vector. And the action of the superoperator on the left and on the right is going to be a linear operator acting in my rho density matrix. Okay? So let's make this clear. So the vectorized form of the first element of my Lindy-Bladder, that is minus I, H, commutator of this guy here, is just the minus I, the vector of H and my density matrix, plus I, the vector, plus I, the vector of, now it's the opposite size, density matrix, the Hamiltonian here, okay? We can simply put the identity here. It makes no difference. We can put also the identity here. It makes no difference as well. And then we use the relation that we know, okay? So then we have minus I that multiplies here. Then I have H transposed, tensor product with the identity, acting on the vectorization of the guy that's in the middle, plus I, and then I have identity, tensor product of the guy on the right, and then acting on my density matrix. At the end of the day, we just have, let me put in simpler form, minus I that multiplies identity times Hamiltonian minus Hamiltonian transposed times identity, that everything acts on my vectorized state, okay? So then we have the first linear representation of my Lindy-Bladder superoperator, but now you see that this is just a matrix, right? It's just a linear operator, and we can do or manipulate this guy. Is it clear, guys? Okay, so I think this is the idea. I'm not going to do the rest because it's just a repetition of this. So for example, the vectorization of L rho L dagger, that is the second term here. It's direct, right? So the vectorization of this guy here is just L transposed, tensor product with the own L dagger, everything here acting on my vectorized state. I'm sorry, dagger times transposed, this becomes the complex conjugated, and then here is just L. See? Yes?
When you do the microscopic derivation, you get a lamp shift on the system, Hamiltonian. And here it does not appear.
I mean, yeah, here is implicit, the lamp shift is implicit in these terms here, for example. Yeah. Yes, yeah. So if you think about the full Hamiltonian system plus environment plus interaction, this is not only the system, okay? There is a lamp shift implicit in here, okay? So then at the end of the day, the vectorized form of my superoperator is just a linear operator that is given by this guy here. So the identity, tensor product with Hamiltonian minus Hamiltonian transposed, identity, and then we have a sum over LK, L conjugated K, tensor product of L, minus half L dagger L transposed, identity, minus half identity L dagger L. Okay. So of course that is not so simple operator as we expected, but in any case, it's still a linear operator, and then we can try to diagonalize this guy here and obtain some further information. So then recall that in general, this linear superoperator here, linear Lindblad operator, due to these L operators or the dissipator operators, is not going to be a simple Hermitian operator, even though we can always diagonalize any non-Hermitian Hamiltonian as well, apart from some specific case. How we do this, we obtain now not only the usual eigenvectors, that is what we call the right eigenvectors of my linear operators, with some corresponding lambda complex values. But now, in order to have a full spectral decomposition, we also need to obtain the left eigenvalues of my non-Hermitian operator. Okay? So usually, right and left, they can share the same complex eigenvalue. And they also can be written in a orthonormal form, in such a way that you have, they are orthogonal to each other, and we have a usual spectral decomposition. In the usual form of Hermitian, this guy is equal to this guy, and there is nothing different for us, okay? But here, they can be rather different from each other, yes? No, here is general. It could be anything, okay? Independent on the form that you put to these L operators, that becomes the corresponding operator, not Hermitian, you can always obtain this eigendecomposition here, this generalized eigendecomposition. Okay? So, an important consequence is that is it possible to show that you always have at least one steady state for my Lindbladian superoperator? Because this is, of course, one required property that there is always a state such that when I act for the evolution on this, there is no evolution at all, right? It's just a fixed point of my dynamics. And just using these simple ideas here, we can show this very easily. So we can just see, or remember that this type of evolution here, it needs to preserve the positivity and the trace of my density matrix, okay? So if I look for the trace of my evolved state, it does not change. This is the rate of change of the trace of my system, and this needs to be equal 0, okay? And using that the first property there, that the trace maps to inner products, I can always put the identity here to make it simpler. So the trace of this to this guy is just the inner product in my extended space of this to this guy here. Okay? I'm sorry. This to this guy here. Is it clear? So here we are asking if there is this possibility or not. If there is at least one state that is not changed during the evolution. It's like a steady state of the evolution. If you reach there, you'll never go out. Okay? In order to show that there is always at least one of these guys here, we just use these properties of the mapping to the extended space. As for example, we know that the trace of the master equation, differential master equation. This is the rate of change of the properties of my density matrix. It always equal 1. The trace is equal 1 at times t and times t plus dt. So if you look for this trace here, it's always equal 0. We can map the trace of two operators, as we did there in the first condition, as the inner product of their corresponding vectorized form. Okay? But now remember that this is going to be 0 for any state that I put in here, because I always preserve the trace of my density matrix. In other words, that for any state rho here, this is equal 0, just repetition. It means that this guy here needs to be the real 0 of my equation. Okay? In other words, you need to have this satisfied in order for the trace preserving property to be satisfied as well. So we are finding that there is always at least one left eigenvalue of my linearized superoperator that has 0 eigenvalue. In this way, the corresponding right eigenvalue is going to have the same 0 eigenvalue, and we show that there is at least one steady state for my Lindy-Blyden superoperator. Okay? So let me call then the corresponding right eigenvalue with the same corresponds to the left identity is what we call as the rho steady state of my evolution. Yes? Here is just a manipulation of the algebra of these operators, actually. Yeah. No, this is a universal truth. Yeah. So it's what we expect also, right? We expect that the dynamics always drives our system at least to one fixed point. And in order to check in somehow if the corresponding dynamics that we found here satisfy this property, we just manipulate some of this property, some of this algebra in the extended space, and it's quite easy to show that there is always this possibility. Okay? But this is general. You can put any L operator. You can even break, let me say, the Markovianity of this master equation by put some negative rates there. That's still a property, because it's only related to the preservation of my trace during the dynamics. Not more than this.
I'm not sure if I understand. You're just saying that the infinite temperature density matrix is a steady state.
I'm just saying that for each left eigenvector, I have a right eigenvector with the same eigenvalue. Okay? And I'm saying that I can always find a left eigenvalue for this operator that has 0 eigenvalue. Okay? This is the left eigenvalue of my, it has no much relation yet to the steady state. But the corresponding right eigenvalue of this guy is going to be the steady state. But this guy here is not the identity as well. They can be, usually it's completely different from the left one. So this is an unusual property of non-Hermitian operators, that the right and the left, they only share eigenvalues, but the properties, they are completely different to each other. As you can see here, the steady state always have the left that is the same for any evolution that you do. It's always the identity. But the steady state can be anything that you want also. Okay, why do I want to do all of these things? Because now I have that my linear superoperator can be written in terms of my eigenvalues, right eigenvalues, such as we do in the Hermitian operators, right? But now the right and left, they can be rather different. And the master equation rho derivative of my state. That was the superoperator acting in my initial state. When I do the vectorization, it just becomes a linear operator acting in my system, Okay, the derivative of this guy, derivative with respect to time. And this is essentially the same that we know from Schrödinger-like evolution. In other words, if I know the spectral decomposition of my corresponding Hamiltonian or corresponding linear operator, I can then solve the dynamics of my system by just making the exponentiation of this guy for the time and acting on the initial condition that I give. Okay? Which in our case is just going to be given by the sum over all of my eigenvalues, lambda n, t. Then we have the right lambda, the left one, with the inner product in the initial conditions for my density matrix. Okay? In other words, I can always write the dynamics as, so when the eigenvalue is equal 0, I have the identity applied to this guy here. That is just the trace of my density matrix. So I just have equal 1 when I have the steady state here. But then I have the sum of eigenvalues that are different from 0 with the corresponding eigenvalues. Lambda t, and then I have C ni applied to R ni, where these constants here, they are just the overlap of the left eigenvalues to the initial density matrix of my system. Pretty similar to what we know from Hermitian, right? It's just that left and right, they can be different, but also that these eigenvalues here, they are not necessarily real all of the time. They can also be complex numbers, okay? So then we can have an interesting interpretation of the spectrum of this guy. No, it's better here. Any questions, guy? Okay. Yes? Vectorized form, yeah. This is going to be very, very different, yeah. Yes, yes. And this something else that it could be Hermitian as well. It could be anything, yeah. If you want to look for a more complex structure, you assume that this L is non-Hermitian, for example. Then the corresponding linearized form is going to be non-Hermitian. And then we're really, yeah. I'm aiming at this case, yes. Okay, yeah. So for example, that this is not always the case, right? But this could be the case if the n of these LK operators, they are non-Hermitian, okay? And then we have a dynamics that's going to be more interesting than when they are Hermitian, okay? So let me say also, this is interesting because when this guy here is Hermitian, you can still have dissipation that the dissipators here, they are Hermitian operators, is what we call as the coherence like open system dynamics. But in this case, you can always show analytically that the identity is going to be the steady state of your system. So it means that at the end of the day, you lose all of your information and you really recover the classical world, Okay. Our goal here is not to recover the classical world, and that's why we're going to aim at these guys here. Okay. Yes. Yes, this is going to be the goal now. Yeah. Yes. They cannot be positive. I'm going to discuss exactly this now. Yeah. I'm not going to prove this, but reasonably, you cannot have this positive. Okay. So then, So then, looking for the spectral properties of this Lindbladian, we see that if we have the spectrum and the eigenvectors, of course, that we know everything that happens during all of the evolution. But usually this is not the case. But we can still interpret in a nice form what is happening if we just looking for the shape or the form of the eigenvalues of my Lindbladian. Okay? So you see that these guys can be either real or imaginary, or both of them. You can have both terms at the same time. The real part, it cannot be positive, right, by physical arguments. Otherwise, this contribution here is just going to diverge for long times, okay? So when we look for the real part of my eigenvalues, you're going to have something that there is always one that is zero, that is going to be the steady state, the one that corresponds to the left identity vector state. So this guy, it's always present, related to the steady state. And the rest need always to be on this negative plane here, okay? But not necessarily they need to also be real. You can also have some imaginary contribution for these guys. So you can have a bit more complex structure for these eigenvalues in this way here, right? And then we can interpret some facts here in the sense that if you look for this contribution of the real part here, it's negative and it's just giving me what's the decay rate of the corresponding eigenstate, right? It's just an exponential of a minus something that decays exponentially with time. So how much you are far from the steady state eigenvalue in the real part, it gives me the idea of the decay of the corresponding eigenspace. But also you can have these imaginary terms here, and the imaginary terms, when they appear in my spectrum, they just add a complex phase for the corresponding eigenvector. So you can interpret this part here as some coherent oscillations in the corresponding subspace, okay? And moreover, if you wait for a very, very long time in my dynamics, let me put t much larger than 1, it means that all of these eigenvalues that are too far from the steady state, they are just going to be negligible in my expansion there. So they are just going to be dead at some point. The only one that's going to be important to describe the long time dynamics is this one that is closer to my steady state, okay? So that's why we also usually call as lambda asymptotic decay rate is equal to this one that is closer to my system. That is the minimum of minus real part of my spectrum over all of my spectrum, just this guy in here. Because at long times, if you know what is this value, you can describe the dynamics of this guy. So at long times, this is just going to be the steady state plus the contribution of the asymptotic decay rate eigenvalues times t, the contribution of the initial state to it, and the corresponding right eigenvectors, okay? Yes. You can have more, and sometimes it's going to be important to have more, especially if you want to make some quantum computation, you want to have qubits, you have degeneracy, and then it's important to have more here. But at least you have always one, yeah, but you can have more. Yeah. No, no. Yes, that's, you can have if they are along this line here. If they have also zero, yeah, no, you can have. Of course, you can have. Yes, this is like if you think, for example, in the simpler Hermitian dynamics, you don't have the dissipations there. It all should fit here, right? And then all of your spectrum, they are just along this line here. Okay. So in other words, it means that you don't have decay. You don't lose information. Yeah, this capture everything. So it goes from the Hermitian closed to the open one. Yeah. Yes. There, I think that for Gaussian states, there are a lot of works, and because usually Gaussian states, they can be analytically solved for this type of vectorization, because at the end of the day, you have a quadratic Lindblad vector form. You should have, is the same, it's going to be the same as in the closed case, for example, that you have energy excitations for Bogoliubov-like. Here you also have Bogoliubov-like excitations in a more weird form, because you have right Bogoliubov and left Bogoliubov as well, but you have a specific structure for these guys, also for Gaussian. For Gaussian, but generally, it's going to be mess. Yeah. Okay, yeah, but in principle, yes, if you have more than one steady states, you can have more of them living here purely in the complex plane. It means that they do not dissipate, but they still can have some coherent oscillations. And this, I mean, let me advance, since we are already discussing here, is that the main goal of this time crystal in open systems, or one way to characterize the appearance of these time crystals, is looking for the spectrum properties. And we always have a finite decay rate, but it could be that when you have more collective interactions between your spins, more and more spins, the decay rate, it becomes smaller. It means that the lifetime of your system, or at least of the asymptotic decay rate, becomes larger and larger. If you have these longer lifetimes associated also with some non-trivial coherent oscillations, then you have a lifetime with non-trivial dynamics. And that's where the time crystal is going to appear. Okay? I'm making some big advances, but I was planning to discuss also in these slides. Okay? Okay, so given that, this is what I want to discuss about this theoretical part. Let's go for the time crystals then. Okay. Okay. So the focus now is to study one specific example of this open dynamics that leads to a non-trivial phenomenon, that is the phenomenon of time crystal. But first, what is a time crystal? So time crystal, just being short here, it's not a very new concept. It's a different phase or a different instance of old Landau symmetry breaking theory, where you have a system or a Hamiltonian that has some specific interactions or some specific symmetries associated to it. But once we break the symmetries, we have these new phases of matter, right? So essentially, we know this from, I'm not going to stay much time here. We know this from ferromagnetics, that we have a spin rotation symmetry, but we can have some configurations that are stable and do not satisfy the spin rotation symmetries. The crystal lattice, right? We have translation symmetries of the interactions, but they have some ordered form. And we have many different possibilities of breaking the symmetry of the Hamiltonian. Spin-dense waves, superconductors, and so on. Of course, two topological phases have appeared, and then in principle, it seems that we don't have any local order in Landau symmetry breaking. But essentially, it's interesting that among all of these different symmetries that you can break in your Hamiltonian, only recently, I would say in 2012, that Frank Wilczek made this question, is it also possible to generate phases that breaks spontaneously now the time symmetry of your system? Okay? And that's what he called as a time crystal phase. So let me just put here his first proposed model, but I out-advanced that does not work because of some technicalities and some approximation that he did. But just to grasp the idea, so imagine that you have a chain. Oh, this is. So if you have a ring of particles, and somehow you have a superconducting phenomena in this ring of particles, but also these particles then they can have some attractive interactions. So then in this case, you could ask or you could argue if is there a possibility that these particles now they lump together, but they still have a continuous dynamics along your chain because they have these superconducting properties, in a way that if you look for an order parameter, such as the density at particles at position x at time t, and some x prime and time t prime, you can see not only ordering in the spatial position of these particles, but also in the time domain. And this time domain would keep forever. It's really stable. In such a way that you have spatial ordering, that's why the crystal name, but also time ordering, that's why the time crystal name, okay? So this was proposed, and then right after it was very controversial, a lot of debates, and many of them was saying that this is not stable. This is not stable. This is going to be very hard. Okay, so let me use this one as well. Okay, so this is not very stable because in principle in this model you would have charged particles that are rotating. At some point they should irradiate. If they irradiate, they lose energy, and then this is not surviving for infinite long times as we expect for time crystals. Okay, and indeed it was later shown that the ground states they were not the correct one. If you look, they were somehow approximated. If you look for the exact one, this is really not happening in this model. And at the end, it culminated in what we call by the no-go theorem, given by Watanabe and Oshikawa, that if you look for ground states of closed systems or thermal states of closed systems, you can never have this type of phenomenology here, where you have both spatial and time ordering for long-range case, okay? So in some sense, it was not good saying that it's not easy to create this phase, but the community actually took the direction that we were looking at the wrong perspective. We should not look at ground states or thermal equilibrium, but we should look at non-equilibrium context, okay? And this was indeed the good direction or the right direction to take. So for example, when I say out of equilibrium context, is either, for example, you prepare your system in an excitation that's not an eigenstate, and then you leave it just like a quench, for example. Or also you can look for driven dynamics. And that was indeed the first works that showed the appearance of these phases. And they looked for Floquet-like dynamics, just like Victor was explained to us, where you have now a discrete symmetry for a Hamiltonian, that it goes back to itself after any multiple of a fixed time. And then looking for this specific driven dynamics with some non-ergodicity mechanisms, it was possible to show the appearance of these Floquet time crystal phases, okay? So essentially, one idea here, this is the experimental realization, was looking for this three-step Hamiltonian dynamics, where you repeat these three steps many, many times, and then you have your Floquet system, where the first step, you just make a global spin rotation around some axis. So let me say, all of the left go to roughly right, and then you repeat this again and again. The second part, you need to add some interactions between these spins, such a way that you want to create a collective phenomenon, not just one single spin that's making some non-trivial dynamics. You want all of them to have a collective synchronous behavior. And then you need to add also some non-ergodicity mechanisms, such as we discussed in the first lecture. If you add some disorder, usually you can fail to thermalize, and possibly you can still have this quantum effect for a long, long time. And that was indeed the case. So if you look at these three mechanisms, apart from this discussion that is MBL really real or not, you can see the stability of these phases. So for example, this was the first experimental realization, 2017, right after the theoretical predictions, where you use these trapped ions or the defects in crystals that act as your effective spins. You apply essentially that Floquet procedure, and here is just the magnetization of each one of your spins during the Floquet evolution. So essentially, here is for a finite chain. You see this up and down, up and down. The spins, they are all up, then they are all down, and they keep this behavior somehow for a long time. But then you see that while the symmetry of your system is that it should go back to itself after one period only, because this is the time symmetry of your Hamiltonian. All of the spins, they are coming back to themselves only after 2 periods. So you have a period doubling dynamics. So then you're essentially breaking the time translation symmetry of your underlying system. So here you still see the decay of these spins because it's a finite chain, you have some imperfections. But if you look for the theoretical proposal, that you have really a closed system, this should be a completely plateau with all of your spins really in a collective breaking of this time symmetry. So I'm going to discuss a bit more about this closed case in the next lecture, because it's going to also be related to the application of these phases as sensors. But for here, I'm going to focus to the open system that is also very interesting. So let me just say that not only many-body localization is possible to stabilize this type of period doubling dynamics, you could use some other ergodicity breaking mechanism as well. As for example, you can use quantum scars, you can use long-range interactions in the spins, you can use Stark localization, anything that in principle would avoid the fast thermalization of your system could try to be exploited here in this case as well. Okay. So, and then these were the first proposals, but then we asked ourselves, what about continuous time crystal? That now you have, for example, a Hamiltonian that does not depend on time, but you want to see some non-trivial dynamics that depends on time, in a way that now you are breaking the time continuous symmetry of your Hamiltonian. And then somehow you need to go, or to avoid this no-go theorem, right? Usually we cannot be in the closed system, because if you have a Hamiltonian that does not depend on the closed system, it's a bit hard to think on ground state. You cannot go. If you go to the excited state, we have this MBL, but everything is somehow static there in the MBL or in some other types of localization. And then the idea here that we took was looking for what we called as boundary time crystal, or essentially our open systems phenomena. Okay. So now we have the system degrees of freedom and the environment degrees of freedom, like the open system that we discussed here. And then we are not interested on the dynamics of the environment degrees of freedom, but we just want to understand how is the dynamics of the system and if it has some non-trivial behavior or not. Okay. So in some sense, we say that it's the boundary, but it's equivalent to the open that we discussed here, because it comes from a node idea of spontaneous symmetry breaking phase, that they can break only at the surface of your material, but not in the bulk of your material. Okay? And then essentially we are automatically out of no-go theorem here as well, because now we have intrinsically non-equilibrium system. We are not looking for the whole properties to break the symmetry. We are just looking for a fraction of it, but it's still a macroscopic fraction of my degrees of freedom. Okay? So there is some possibility, at least in principle, to have a non-trivial dynamics for this guy. So specifically what we look is that system that while the environment is completely trivial, they are static, they are roughly unchanged. If you look for the open part or the boundary part, you could have some macroscopic order parameter that has some non-trivial oscillations, some non-trivial dynamics that persist forever in time. Even though the whole Hamiltonian has no time dependence, you could still try to look for time dependence in a part of it. Okay. And of course, this needs to be a many-body phase. It's not just a single spin processing. This is not a phase. This is not a time crystal. We want that the whole system be a collective processing or a collective motion or interacting motion, okay? So we need that both the system and the environment to be macroscopically large, But of course, that the environment can be much larger than the system in a way that this ratio goes to 0. And then we ask, is it possible then that this type of phenology appears in this Lindbladian dynamics that we just described, in Markovian system with these specific spectral properties? And the answer is yes, yes. And it's very interesting to understand why it can happen in some class of systems. So one class of system that was found is these dissipative models, the Lindbladian dissipative models, where you have now collective interactions in your dissipation, and then you can induce some cooperative interactions or cooperative motion of all of your spins. So the idea comes somehow from old phenomena, if I remember well, in the 70s, where, for example, if you look for a bunch of atoms, and they are somehow sparsed from each other, they are not very close to each other, we know that they interact with the quantized electromagnetic field, and at some point you have spontaneous decay of these atoms. Okay? And if you look for a detector for this rate of radiation, it's just going to be the exponential that we discussed here. So there is this radiation over time exponentially fast. Okay? And this happens for ordinary fluorescence phenomena, for example. Where the atoms spontaneously decay, you can assume that they do not see each other, and you have this isotropic and constant radiation. But now imagine the different situation where these atoms, they are very close together in comparison to the photon's wavelength. So essentially, they try to see, or they see the same mode for my electromagnetic field. Okay? In this case, if you put this detector to see how is the radiation occurring in your atoms, you see a very, very different phenomena. You see that instead of this isotropic and constant exponential radiation, you see that the radiation actually is increased with time up to a peak, and then you start having less and less radiation. So in some sense, the radiation here occurs much faster and also much stronger in a very short period of time. The time here is essentially inverse to the number of atoms that we have in a system. So if you have really a big ensemble of atoms that are close together, you have this burst of radiation in a very short infinitesimal time step. Okay? And this occurs essentially because now the atoms, they somehow interact to each other, mediated by the electromagnetic field. Okay? So all of them, they see essentially the same electromagnetic mode. They interact to this electromagnetic mode to have the spontaneous decay. But since all of them, they interact to the same, it's something that this interacting mode also mediates some effective interactions between your atoms themselves. Okay? You can think, for example, in the classical world, you have those pictures of a pendulum, right? With a pendulum with many balls. And if they are coupled to the same support, once one move, it can move the support, and it can affect the other pendulums as well. So you have this mediation of the support into the dynamics of all of your balls in the pendulums. This is essentially the idea behind, but in a quantum form, of this superradiance phenomenon. Of course, that making these phenomena is not easy because you need both to have many atoms together, and they need to interact to the same electromagnetic field. And usually, the interaction of an atom to an electromagnetic field is very, very weak, okay? Especially if you are in the vacuum space, or if you are in the real space, it does not occur in a good rate. So one major difficulty of this cooperative phenomena or collective phenomena is to strengthen the coupling between the atoms and the corresponding electromagnetic field. And one way to improve these interactions is using what we call as cavity QED. Okay? And then the idea is that now you can use optical lattices to trap your atoms in a very small volume. Okay? So you cool down your atoms, you laser on your atoms in a short region such that they are somehow close together, and then you put in a cavity. And the cavity has two mirrors, such that if you apply a laser light into this cavity, the laser is going to bounce many, many times into the same region where your atoms are trapped. And then essentially, you are allowing to have more times interactions between your atoms and this bouncing laser field, okay? And then in some sense, if you have some very good mirrors in your cavity, you improve the interactions or strengthen the interactions of your effective atoms here to the modes of your photonic modes of your cavity, okay? And these, you also have a high precision in the manipulation of how to tune the electromagnetic modes to the atomic levels in such a way that they get in resonance and improve even more this spontaneous emission that occurs because of this coupling. Okay, and indeed, I mean, this was the Nobel Prize in 2012 by Aroshi and Weineland that essentially for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems, especially in these cavities, QEDs. Okay, and of course that it can be used not only to discuss about this time crystal that I'm going to say here, but also many applications in quantum information and computation, also to simulate some long-range interacting system, because now you have a photonic mode that can mediate interactions between all of your ensembles there, right? And then you are essentially simulating long-range interactions between your spins or your atoms. Okay, so consider now a simple instance of these cavities where you have a single photonic mode in your cavity, and you have a bunch of n spins that interact to the same photonic mode. So your Hamiltonian then is just some electromagnetic field along your spins, for example. But then you have this interaction of all of your spins. Once they have a spontaneous decay, you create, here it should be a creation operator. You have a creation of a photon in the cavity, or if these atoms, they absorb the photon, they have a uppering operator, or they are excited in my ensemble. But then you have here the sum over all of my spins with the same rate to the same photonic mode. So this is somehow a all-to-all coupling of my spins to the same photon. And on top of that, also you can have some imperfections in the cavity in a way that the photons, they are not completely trapped in the experimental platform, but they can also, at some gamma rate here, to escape from the platform, and then in the language of the Lindbladian master equation, you just lose photonic particles to the external environment, okay? Then looking for what we call as a diabatic elimination of cavity, that is just, as we did, tracing out what we don't want to describe, that in this case, we don't want to describe the dynamics of the photonic modes. And then we trace out in this specific limit that we call the diabatic limit, we have an effective dynamics for my spin-only degrees of freedom. And then we can understand or analyze what are the properties of the corresponding spin Lindbladian. Okay. So in this case, you can show that the corresponding Lindbladian has this form here. And then we go back to our discussion, where the first term here gives us coherent evolution for my spins, all of my spins. Now is always a collective operator, acting all of my spins in an homogeneous form, either along some direction or some decay or some excitation. Then we see that we have this coherent magnetic field along an x direction, but also it's competing with an effect decay because I'm coupled to the photonic modes. But you see that the effect decay is given by this jump operator, or this Lindblad jump operator, that makes the decay of all of my spins at the same time, in the same idea as this superradiance phenomenon. It's not that just one or the other that is making decay, but they see each other, or they make this cooperative motion, okay? This type of model was actually studied a long time ago also, in the 70s, but at that time they were more interested on what are the steady state properties of these dynamics. They were just looking for the infinite long time the system has stabilized and for what properties it has stabilized. And then we have this phase diagram essentially here. So here is 600, but it could be more than this. It's qualitative the same. But you see this phase transition in the model, where if the coherent term is stronger than the dissipative term, you have that the system has some finite magnetization along the z direction. But on the other case, where the dissipative part is very, very strong, then your system is really going to have a stronger decay to the ground configuration. You see that the magnetization has this non-analytical phase transition here, and then the magnetization is essentially 0 in this other part of my phase diagram. Okay? But these are static properties, and here we are going to be interested in the dynamical properties. So what about dynamics? And then, before going to the model, we can essentially understand the dynamical properties from this perspective, or the spectral properties of my corresponding Lindbladian superoperator. And then if you are in the two parts of my phase diagram, either you are here or you are here, you see different spectrum for my eigenvalues. Okay? So here I'm just showing the imaginary part of my eigenvalues and the real, and exactly this picture here. All of the real parts, they are negative, but you can also have some imaginary terms for these eigenvalues. If you are in the, let me say, trivial phase, where the dissipation is very, very strong, you see this shape for the eigenvalues, and if you look close for those that are the asymptotic decay rate, the ones that survive for a long, long time, they only have essentially a real term for these dynamics. On the other side, if you look for the other part of the phase diagram, dissipation is not so strong, but it's still relevant. You have somehow a different shape for the eigenvalues, but then you see that these ones that are closer to 0, some of them, they can still have some imaginary term there. So in the words that I'm saying here, it means that we can have possibility of a coherent dynamics for the long time dynamics. So taking a better or more quantitative analysis on the trivial part, we can make a finite size scaling of these first eigenvalues here. And here I'm just showing how these first ones, they change with the number of particles in my system. So if I increase the number of particles, I'm going to the left on this figure here. And you see that j equal 1, for example, is this one here, is the smallest one. You see that it actually increases, but then in the thermodynamic limit is when I touch 0 here, it goes to a finite value. So it means that even if I have a very long or very large ensemble, it still have a finite lifetime for the decay towards the steady state. Okay? So we say that we have a gap at the Lindbladian, and therefore an exponential decay towards the steady state. Moreover, in this case, we don't have imaginary terms for them. And as we perhaps already know what's going to happen in the time crystal phase, if we make the same analysis of finite size scaling for the gap or for the eigenvalues, we see now, okay, so j equal 1 is again the red one, is this one that is closer. J equal 2 and 3 and 4 are those that are also close to 0. But now we see that when we go to the thermodynamic limit, enlarging the ensemble, these eigenvalues actually decay. So it means that the lifetime of this eigenspace is going to increase and increase and increase to the time that when you go for the thermodynamic limit, the lifetime also diverges. And then we have a non-thermalization of our open system dynamics. But of course that we are interested not only on an infinite lifetime, but also we want to have some coherent oscillations, some non-trivial dynamics for the corresponding state. And here we make the same analysis. We look for the imaginary eigenvalues of my spectrum, make the thermodynamic limit, and you see that the imaginary eigenvalues, they come in these blocks here, in this frequency or well-defined structure, such as I think that Pedro was asking for some type of structure like this. So you see that you have gapless, but you also have coherent oscillations related to this subspace. And in principle, this is what we want for a non-trivial dynamics. If you look then for the real dynamics, you just initialize your system in some configuration. Here, for example, all of the spins, they are pointing along the x direction. And you run the code, and you see the corresponding magnetization dynamics, for example. You see that if you have a finite number of spins there, for example, 40, they are going to have some coherent oscillations, but of course the gap here is still finite, and at some point it goes towards the steady state, and these oscillations, they essentially die. But as we increase the number of spins, we know that the system becomes more and more gapless, and the correlations now becomes more and more strong, or the cooperative motion becomes more dominant in my system. And then you see that these oscillations, they still decay, but they decay in a slower rate, up to the point that if you go to the thermodynamic limit, you have some persistent oscillations that perdure forever. And then you have the appearance of the boundary time crystal in your system. Okay. Okay, so, and now here's just some illustration that I find interesting for this model here. Can we understand easily what happens in the thermodynamic limit? And we always have this type of approach of mean field that is very helpful to grasp in a simpler form the properties of my system. Right? We can also apply the mean field here. That is nice. In this following sense, we go for the Eisenhower picture, where you have the Lindbladian evolution not for the density matrix, but we have for spin observables or any Hermitian observable. You see that it has similar shape as the Lindbladian master equation, apart from a plus I here instead of minus I, and the L dagger, it's in a bit different structure. But then if you use if you apply this Eisenberg evolution for some observables, let me say the magnetization along X, just forget these terms here, they should not be here, but you just see that the coherent Hamiltonian is going to lead to this only term here, and the dissipative kappa is going to lead to these new terms here, okay? And you can do this for any observable. So if you look for any direction of your magnetization, it's going to depend on one body collective spins, two body collective spins. But then to understand the dynamics of this guy, you need to understand then what's the dynamics of two body. Then you obtain the Heisenberg evolution for the two body. You're going to see that depends on one body, two body, but now the three body has also appeared. And you can continue this mess as you want. If you want to understand the two body dynamics, you need to understand the three body. If you make the Heisenberg for three body, you're going to see that appears a four body. And this hierarchy, it goes forever. It never ends till you reach the full Hilbert space or the full operators. So what the mean field makes simpler is that, okay, so let's assume that the two body can be reproduced by a product of one body. And then essentially, I am closing this full hierarchy in just the first line here. Because now, this one that would depend on the two body does not depend on two body anymore. It just depends on one body because I'm associating this guy here to simpler one body dynamics. Okay? I'm not going to details of the mean field, but at the end of the day, it's just make this cumulant closure that leads to this set of simple differential equations for my magnetization along X, Y, and Z direction. And then we just need to solve a classical three variables differential equation in order to obtain the full dynamics, okay? So one nice form to see what's happening there, we just plot now the Poincare section, for example. We look for classical like phase variables as the position and momentum in terms of the magnetizations along the Z and X and Y, and see how they behave in the dynamics of my system. So this Poincare section here is just you initialize your system with a fixed Z, X, and Y magnetization. So you are in one point of this figure here, and then you let the dynamics to evolve. And then you see how is the trajectory of this dynamics. And what is interesting is that if you are in the time crystal behavior, where the dissipation is smaller than the coherent part, you see that independent on the initial condition that you give to the system, it always goes into this orbits, closed orbits. It means that your spins, they are always oscillating in a fixed period and a fixed oscillation, okay? And you can also then play with some other types of Hamiltonian to see, in order to see if this is robust or not. For example, you can add some interactions of the Hamiltonian along Z and X. You see that the Poincare section, they change a bit. Now it depends on the initial condition that you give to your spins. So if you give, for example, a momentum that is too low, they are going to be approaching this steady state that is trivial. Then you just got fixed here. There's no non-trivial dynamics anymore. But if you have a higher initial momentum, you are still trapped in this oscillatory motion or in the time crystal dynamics. So I think that I'm passing somehow the time. Perhaps in 5 minutes I can already finish, because then we already go to the conclusion. So the idea then is to show this Lindbladian master equation, but also discuss some non-trivial phenomena. That is what we call as boundary time crystal. So while these discrete, they appear in closed, continuous seems to be more likely in open. And then this dissipative collective models is one instance of these guys. Of course, that we are always asking if are there also other types of boundary time crystal that do not depend on this cooperative collective dissipation. This is still, I would say, an open question. And of course, if some dissipative topological system could show also some type of similar phenomenology. I'm going to discuss about the dissipative topological systems in the last lecture, but they seem also to have these properties, the spectral properties of gapless excitations with the possibility of coherent terms as well. Okay? And of course, I mean, why should I care about this phase? For some years, I mean, it was just a matter of curiosity and fundamental theory to understand if there's this new phase of matter. But now I think that we're moving to possible applications of this non-trivial phenomenon as well, such as in sensors that I'm going to discuss as well. There are some works on quantum engines that operate with these persistent motions. We have some works also, or some projects using them as clock. So this is perhaps very natural, right? To have something that is very stable, very robust, and it has a very fixed periodicity. So you can think of how I can exploit to make a clock out of it. And also some works using these things for simulating complex quantum networks. Okay, given that, I thank you for attention, and we can stop it here. And okay, questions, yeah. So when you say one dimension, you say like a chain of particles. So in principle, the first proposal by Wilczek, he was really thinking on breaking both spatial ordering, and then you have the crystal, an ordered form, and also the time, where these atoms, they have some non-trivial dynamics. That's why you have the time and the crystal also in the name, okay? But essentially, you can think of just having a time-ordered correlation. You don't need to have a spatial organization of your system. Yes, a structure appears in the time axis, in this one dimension. This is sufficient for a time crystal. With what, I'm sorry? Okay. But this is a non-equilibrium phase, okay? This is very different from equilibrium, Landau's symmetry breaking theory. Yeah, I think that's it. Yeah. Yeah. So I think that there are two things. Yeah, the first is that this is intrinsically non-equilibrium, and specifically for this model here of the boundary time crystal, you have infinite range interactions, not only long range. It's really all-to-all interacting to each other because they are mediated by this photonic mode. Okay, so essentially, when you go for the jump Lindblad master equation, okay, this is different from applying the lower operator on each of your atoms individually, because this is making a full sum over all of them in a collective form. So somehow they see each other in an infinite range form. Okay, and then it goes again out of the Mermin-Wagner theorem. Okay, that's why I also put as a conclusion here. Oops, I went to the wrong way. If it's also possible to observe this phenomenology in some other models, as for example, those that could have some shorter range interactions. And in principle, I mean, there are some works along these lines here. where you have now that each one of your atoms, they interact to one reservoir. So they have a specific jump operator for each one of your constituents. But then you need to go for 2D systems. And if you make a mean field approach for the dynamics, you see these limit cycles or you see these periodic dynamics there, a la time crystal as well. But there is still the question is this just because we're doing mean field, or is this really there if we make some exact evolution of the system? And since the exact is very hard to do, it's still an open point to be addressed. Okay. Yes.
Kind of going along the same line, so like, this isn't continuous time translation signature breaking, right? This is discrete.
So here is a continuous because your Hamiltonian has no time dependence. And the period here, it continuous varies with dependence of your coupling parameters. Okay.
Yeah, well, I see, maybe because I thought you're in an optical cavity with a laser, right? The laser breaks time translation signature.
Yeah, but here you can go even to the rotation frame of your laser that you see that is not this time that appears here. It's not this periodicity. It's not because of rotating wave, not rotating wave, but a rotating frame framework. Okay. Yeah, but that's true. Yeah, you are in the laser cavity. At least in experimental proposal, you would be in a laser cavity. But even you could forget about the laser cavity. You can just think about the Hamiltonian, and you see that the Hamiltonian you can construct in a time-dependent form as well. If you think experimentally, yes, this is going to be important, right?
So like this is an analogy then of like a charge density.
Yes. Then you have a continuous parameter that is breaking. That is the order parameter for your system. Yes. 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 I would say so, yeah. Yeah, but I cannot see how if you, no, yeah, I would say so, yeah. Because the gap, when you talk about the spectral properties, you can forget about physics in some sense, right? I just want to understand if for long times, I still have, for long times, I mean infinite long times, I still have some dynamics in my system or not, okay? And if I don't have this, the first eigenvalue becoming 0, it's always finite. It means that for infinite times, you always destroy this guy here. But of course that you could still argue, okay, but I have this case, right? I have some other eigenvalues here that has some coherence terms, right? But then it's a bit tricky to say that this is going to be a time crystal or a spontaneous symmetry breaking phenomena, because when we talk about symmetry breaking phases, it means that these phases, they become stable only when you go to the thermodynamic limit, okay? But if these coherent oscillations, they are here even for finite system, then it's a different thing that's happening there, for example. So you can think that, for example, if you have just one spin that do not interact to anybody, but it feels some magnetic field. So it's going to be processing there, right, forever. And then it's going to appear some eigenvalue here in your spectrum. But it's just one spin that is processing. It's not really a many-body phase. So that's why, it's important to have the gapless, because it also gives the notion that it's because somehow of some collective interactions or some many-body interactions that the gapless nature is appearing. It's because everybody is now trying to synchronize in a better form their motion. Okay. Yes, Fisher zero-like, exactly. As Hoyos presented at the beginning, yeah. Okay, I think that I already passed many time. Okay, so thank you guys.